Okay, everybody. We hinted at this in the last video, the last instructional video. We're going to be talking about functions, in our case, in linear algebra transformations that are one-to-one and onto. Okay, just like functions, these transformations in linear algebra can be either one-to-one or onto or both. So go ahead and get MATLAB open and get section 3.2 in the online notes open. So pause the video and get that ready to roll. And the first one is, first thing I'll just throw out as a vocab word. So an injective function is a one-to-one function. And what does it do? It maps distinct elements of the domain to distinct elements. It's one-to-one, just like it sounds. It maps a single preimage to a single image. So you don't have two things in the domain getting mapped to the same place in the range. They have to be mapped to distinct elements. Okay. Then we have this huge theorem. Okay, and the key to understanding the theorem is this statement. The following statements are all equivalent. In other words, any of the 7 statements implies any of the other 6. And the one that's most important, I've marked in red, because this is the easiest thing to check. We row reduce matrix A and see how many pivots it has. Okay, that seems pretty reasonable. I will mention this, that a one-to-one function maps the 0 vector to the 0 vector. Notice this trivial solution, right? The only solution to a times a vector x equals the 0 vector is the 0 vector itself. So notice that a one-to-one matrix transformation maps the 0 vector to the 0 vector, and that's the only vector it maps there. And then the columns of a matrix are linearly independent. Notice that this is essentially the definition of what it means to have a pivot in every column, right? All the pivots indicate columns that are linearly independent. So if I have 3 pivots in a 5x5 matrix, the 3 columns that the pivots are in, those columns are linearly independent if I treat them as vectors. So 5 and 6 mean exactly the same thing, and then 4 here is an interesting fact of one-to-one matrix transformations, that the 0 vector gets mapped to the 0 vector. All right, so taking that all in, let's get rid of the ink and move on to onto. So whereas one-to-one is called injective, onto is called surjective. So injective and surjective, and if it's both, it's called bijective. All right. And if every element of the codomain is a value for some element of its domain, so the codomain is covered if the transformation is onto. All right. But let's zip forward. Oh, here's another huge theorem. And just like before, the second and third items are basically the definition of what it means. And again, the one in red that I've identified, that's the easiest one to check. So when we are going to want to check whether something's onto, we're going to row reduce it and count how many pivots there are. And if there are pivots in every single row, we'll know that it's onto. If there are pivots in every single column, we'll know that it's one-to-one, which I believe I have summarized right here. Yeah, there we go. So this is a fairly straightforward task, right? Just row reduce the matrix and see where the pivots are. Pivots in every column, one-to-one. Pivot in every row, the transformation is onto. And then it turns out that we have 4 examples. If you look in the online notes, you'll see that we have these 4. And I actually copied this right out of the right off the online notes, right? We have A, we have B, we have C, we have D. And let me go ahead and run this so that we load all of these matrices into the computer's brain. And let's row reduce A. Okay, so REF of, oops, I cannot type. All right, REF A, boom, and run this. Now, by the way, if you look at A, and I'll take his semicolon off so you can see it. So A is a 3x2 matrix. It's taller than it is wide. So if you think about it, it can't have a pivot in every column. There's just no way. It might be excuse me, it can't have a pivot in every row. It can have a pivot in every column. As a matter of fact, it does. But it can't have a pivot in every row. So it's got a limitation. It cannot be bijective. It can't be both one-to-one and onto. But we see that it does in fact have a pivot in every column. If it has a pivot in every column, that means it's one-to-one, right? Well, we'll take a look in just a second. All right, and we can row reduce the matrix B. And notice that we get the identity matrix for 3 by 3 matrices, okay, and again, these columns are the standard basis, and we have a column in every, we have a pivot in every column, and we have a pivot in every row, and that means it's bijective. It's both one-to-one and onto. So you see, this is a pretty straightforward process, and I can row reduce C, and oh, so this is interesting. I have a pivot and a pivot and a pivot, so I have a row with no pivots, and I have a column with no pivots. So this is neither. C is neither injective or surjective. It is neither one-to-one nor onto. Let me get rid of the ink and move down, and we can row reduce F. Excuse me, we can row reduce D. Now this is interesting. I'm going to have to actually look. I have pivot, pivot, pivot. So it's pretty clear that there are 2 columns that don't have pivots. But check this out. All my rows do. I have 3 rows and 3 pivots. Okay, so what does that mean? Well, the columns don't all have pivots, so it's not one-to-one, but the rows all have pivots, so it's onto. So the transformation that has the associated matrix D is onto. And this is all summarized for us. Hopefully you followed along with this work, but I went ahead and put it in the PowerPoint, right? So we row reduce and we find that there is a pivot in every column, right? So it's one-to-one. Okay. And then with B, when we row reduced and we got the identity matrix, it's both. So it's both one-to-one and onto, or if you're using the injective and surjective, it's a bijection. Okay, both one-to-one and onto. And then with C, we row reduced and we only got 3 pivots, and we have both 4 rows and 4 columns. So this can be neither one-to-one nor onto, because it does not have pivots in all its rows and it does not have pivots in all its columns. And then for D, we found that it had pivots in all of its rows, but there are 2 columns that do not have pivots, therefore it's onto, but not one-to-one. Okay, so once again, a fairly straightforward application of row reducing. We can tell whether the function is one-to-one, onto, both, or neither.